So we're up to the last part of 16.7. Is it 5? I'm not sure. There's been a break in my recording of these videos. So let's review a little bit. Recall, we've been talking about surface integrals of vector fields. So the double integral of f dot ds. And we've said that this, comes down to the double integral over the surface of f dot n ds. And that we further break this down or rewrite it into the double integral over a plane region A of f dot ru cross rv dA, where r gives the surface S that we're integrating over, and A is in the plane, either the UV plane or the XY plane. It's in the XY plane if it turns out that S is the region of S that we're interested in can be given as a function of X and Y. And in that case, this cross product here we know is the square root of a certain expression. So we've got these special cases. What I really want to say here is that most of the time we're down here. We use this expression, but I'm going to suggest that when you're on a sphere, you're up here. I rhyme. So let's talk about how all of this plays out for the special case of S being a sphere. Let's first talk about the normal vector to a sphere, and just recall that it's not different from the circle case. And let's recall the circle case. So if you have a circle and always an interesting see how close I can get here. So if we have a circle that a normal so here at the point xy on the circle, recall we showed a long time ago that the vector xy is normal to the circle at the point xy. So at the point xy, the vector xy is normal to the circle. And of course, unit normal would then just be xy over magnitude of xy. Well, the case for a sphere is along those lines. Finally, towards the end of my career, I've learned the appropriate cheat for sketching a sphere. You do it in the XY plane and you simply explain Z axis comes out of the paper. So in other words, I don't really draw So z-axis comes out of the paper towards the viewer. Always looks wrong. So in other words, I just draw a circle and then draw that. So let's say this is a sphere of radius A. Of course, centered at the origin. And again, the vector that points from the origin to any point x, y, z on the sphere, that vector will be normal to the sphere at x, y, z. So x, y, z is normal to the sphere at the point x, y, z. And let's just translate all of this into our way of parameterizing the sphere. So we know that we can give r as a function of phi and theta. So a here, the radius of the sphere is fixed, so it's not a parameter, so we'll express it like I did here as a. So this is a sine phi cosine theta, a sine phi sine theta, and a cosine phi. This parameterization then traces out, is trace the right word, the sphere? What's the magnitude of this vector? The magnitude of this vector is a. So, but we can factor that a out. So this is a sine phi cosine theta, sine phi sine theta, and cosine phi. So since we know that the entire vector is normal to the sphere and is of radius a, and then we factor that a out, this must be the unit normal. So unit normal to the sphere is then n equal to sine phi cosine theta, sine phi sine theta, cosine phi. But if we're just kind of going directly and doing it up here, we then need this differential of surface area. And I'm just going to kind of summarize what the book does in example 10, section 16.6. I could go through all the details. I promise you I could. I've got it all in my notes here. But let's just summarize it and get the main points. I mean, what you're looking for here is, remember, ds is, it's the r, it's the magnitude of RU cross RV dA. And that magnitude canceled out down here, which is usually why this is simpler. But in this case, it's better to go with the other way. So if we just summarize magnitude of R phi cross R theta, it's, you know, you compute R phi, you compute R theta, you take the cross product, you eventually get that it's A squared sine squared phi cosine theta, A squared sine squared phi sine theta, A squared sine phi cosine phi for the z component there. And then again, another not overly short computation to get the magnitude. And you should go through this. You can, you know the computations you're supposed to do to get these. So do it and check your work against the book in 16.6. And you get a squared sine phi here. So then for a sphere, you compute the double integral over A of f dot the unit vector, which is sine phi cosine theta, sine phi sine theta cosine phi times a squared sine phi. Don't need the absolute value there. And then dA, where now dA is, remember, dA is no longer, it's not the, we've already got all the, you know, the differential of volume that you got from spherical integration, that's already over here. Remember, when we were integrating in 15.8, it was rho squared sine phi d rho d theta d phi. Now we don't have the d rho because that's just A and it's a constant. So this just ends up being dA is just d theta d phi in whatever order makes most sense. Okay, so then 16.7 homework is 5 up to 29, the odd numbered problems. And we got 2 sections to go, 2 real sections, 16.8 and 16.9, each introduce 3-dimensional versions of the 2 versions of Green's theorem in the plane that we looked at earlier. There is a 16.10, it's just a 1-page summary of some of the important integration results. So